So lesson number 1 in our exponents and log functions chapter starts with a review. So we're going to review the exponent laws, and then we're going to use the exponent laws. So the exponent laws involve operations on powers, and so this part here should be a review of things that we've done in grade 10 and in grade 11. So we're on page 191. So exponents or powers are just a way of shortening repeated multiplication. So instead of going 3 times 3 times 3 times 3 times 3, I can go 3 to the power of 5. It means the same thing. So within my power, I have my base and I have my exponent. Bases don't have to be just numbers. They can be variables. They can be fractions. They can be decimals. They can be negative numbers as well as positive numbers. My exponents, for the most part, we restrict our exponents to positive or negative numbers. We can have decimals with our exponents. We did do some decimal work in the past. So if we go through the exponent laws, if I had something like 3 to the power of 7 times 3 to the power of 5, and I wanted to simplify it as 3 to the power of something, what would that something be?
12.
12. What did you do?
Add the exponents.
So when the bases are the same, I can add the exponents. So this would become x to the power of m plus n. So I would add the exponents. So the quotient law, bases are the same, and I'm doing a division. So if I had 3 to the power of 7 divided by 3 to the power of 5, what would I get? 3 to the power of 2. So what am I doing to my exponents? Subtracting them. So I get x to the power of m minus n. Power of a power looks something like this. I have 3 to the power of 5 raised to the power of 4. So what that means is I have 3 to the power of 5 multiplied out 4 times. What would that simplify to? 3 to the power of what? So if I have 3 to the power of 5 4 times, my multiplication rule says I can do what to these exponents? So if I add them together, what do I get?
20.
20. Is there any way I can go multiply them? So I can multiply the exponents. So this would be x to the power of m times n. Power of a product. So if I had 3x to the power of 5, what does that mean? So 3x to the power of 5.
X 5 times?
Not just the x 5 times, the 3x 5 times. So I have my x to the power of 5, but I also have the 3 to the power of 5. Typically, I would take this and I would actually simplify it. I would figure out what is 3 to the power of 5, and I can use my calculator to help me get that. I think I get, what do I get? 243? So that's how I would write it in simplified form. But what it means is this 5 is going to both parts inside the bracket. So my x times y to the power of m would become x to the power of m times y to the power of m. And the same thing happens with a quotient. So whatever's inside the brackets, the exponent applies to everything inside the brackets. X to the power of m over y to the power of m. Why do I have that y can't equal 0? What happens if y equals 0 in that question? Why can't I do it? Yeah, I can't divide by 0, so that's why the restriction is there. Y can't be 0 because then I can't actually solve this question. Then we have the integral exponent rule, x to the power of negative m. How do I make that a positive m? You have to put it on the bottom. So I get 1 over x to the positive m. And I'm going to take a moment to show why that happens. If I had something like 3 to the power of 5 divided by 3 to the power of 7, my quotient power, or my quotient law, says I can subtract these, and that's how we get negative 2. Okay? If I were to expand these out, this is what I get when I expand out my 3's. What's 3 divided by 3?
1.
1. What am I left with on the top?
0.
Nope. These were all 1's.
Oh, 1.
I'm left with 1 on the top. And then I have 2 3's on the bottom. 3 squared. So if my subtraction law says I get 3 to the negative 2, if when I simplify it I get 1 over 3 squared, these have to be equal. These two statements have to be equal to each other. Okay? This also goes in reverse, meaning if I have, and we're going to put it on this page, if I have 1 over x to the negative m, that becomes x to the positive m. So it goes both ways. If the exponent is negative in the denominator, it would be positive in the numerator, and vice versa. And then we have the rational exponents. These were the ones that I could rewrite as a radical. Does anybody remember how I write them as a radical? So I use my radical symbol. My base still stays the same, but where do my m and my n go? Okay. On your calculator, what is the square root of 9?
3.
Okay. Now I want you to calculate 9 to the power of 1/2. Put the 1/2 in brackets when you put it as an exponent.
3.
What's the cubed root of 8?
2.
What about 8 to the 1/3?
2.
Is there a pattern that you're noticing? If I go back to my fraction here, m over n, where does the n go? So by front, you mean here? Yeah. We call that the index. So it becomes my index. And then the m just stays as my exponent. So I'm going to rewrite this because it's a little bit squished. There's 2 ways I can write these. I can write it as the nth root of x to the power of m, putting that exponent with x. Or I can say take the nth root of x and then raise that answer to the power of m. They mean the same thing. The reason why they're done separately is more so because sometimes I can take the nth root of x and work with that smaller number. Whereas if I take x and I raise it to the power of m and then I have to nth root it, I'm more likely going to have to use technology, my calculator, calculate it. Okay, so now we're going to go through and do practice. 5x squared times x cubed, what would that be as a simplified power? X to the power of what?
5.
Okay. If I have x to the power of 6 divided by x squared,
4.
x to the power of 4. 5x to the power of 5, which is then raised to the power of 4.
X to the power of 20.
Okay? And if I have x over y to the power of 3,
X to the power of 3 over x, or y to the power of 3.
yep. And if I have 3x to the power of 3,
3 to the power of 3 and x to the power of 3.
okay, with this, I would simplify that. So what is 3 to the power of 3?
27x to the power of 3.
So 27x cubed. Okay, so let's look at number 2. Write each of the expression without the use of brackets and making sure you have positive exponents. That's okay. You can come get it from me at 3:30. How do I make this positive?
1 over x to the power of 3.
That's how it becomes positive. Okay, so if I look at the next one, 4x cubed times 2x to the negative 4. So what do I do with the coefficients, the 4 and the 2? Anything special or? What operation's being done? Multiplication. So if I multiply them, Pearl? 8. What's being done with the exponents?
They're being added.
They're being added. So when I add them together, Carcy?
-1.
Okay. But I can't have the -1. So how do I make the -1 positive?
Go under 1.
So I move it down. Where does the 8 go?
Bottom.
You leave it up to
Why do I leave it up top, Josh?
because it's not with the x.
It's not with the x. It doesn't have a negative exponent. The negative exponent is with the x, not with the 8. Okay? If it was written like this, then the whole thing would go down. But it's not. Okay? Okay, what about C?
Here then multiplying 4 and 3.
Okay, so if I multiply the 4 and the 3, I get,
12.
okay,
And then you multiply the 2 by 3.
To the power of 3.
You simplify them.
okay, so what do I get when I simplify it? It's 2 times 2 times 2.
8.
8. Okay. We have to watch out for those because it follows our sense of logic to want to say, well, I multiplied the 4 and the 3, I should just multiply the 2 and the 3. But it's not. It's being multiplied out 3 times. So that's why I get the 8. What about D?
Could you start by doing the exponents?
Yep. Okay, so multiply the exponents, what do I get? Okay. And what about this 3? What do I do with? To the power of 3. And the 5 stays on the outside. So what's 3 to the power of 3? 27. So I have 5 times 27x to the power of 6. But I'm not supposed to have brackets, so what do I do with the 5?
Multiply it in.
Okay, and what do I get when I multiply it in?
135.
I have a trick for you. What's half of 27?
13 and
And what's 13 and a half times 10? 135. So there's a multiplying trick that you can do where if I take half of this number and double that number, those two numbers have the same product as these two. So I can multiply by 10 easier than I can multiply by 5 if I take half of this, if I can do half of that. Okay, so what do I do with E?
So you could go -3 minus -2.
Okay, so what is -3 minus -2?
-1.
Okay, and then how do I make that positive?
Is the 5 with the x in it?
You tell me, is it with the X or not?
It's
How would I know it's with the X?
brackets.
I'd need brackets. If I protected this with brackets, the -1 would go to everything inside. So is the 5 with the -1? No. So the X moves, but the 5 does not. Okay, what about F?
Well, 3b's gonna have an exponent of 1, so you
Yep.
just subtract them.
Okay, so if I go -1/2 minus 1, what do I get? Not -1/2. -1/2 minus 1, and 1 is like 2 halves. So if I have -1 minus 2, I owe you $1 and I borrowed 2 more dollars. Now I owe you -3. So I get -3 halves. So I get b to the power of -3 halves. What about the 12 and the 3?
Divide those.
And what do I get?
4.
Okay? And then how do I make this -3 halves positive? What do I do?
You go 2.
That's putting it as radical. I don't want it as radical, I just want to leave it as an exponent. So how do I make this exponent positive?
Put it on the bottom.
Put it on the bottom. If I wanted to write it as a radical, Marcus, then I could write it as a radical. Once I put it at the bottom. So the cubed would stay with the b. And do I need to put a 2 here? No.
No.
No, because it's already, that symbol itself without an index means the square root. Okay. 4 more questions. I think I missed one on the chart here. No, we didn't. No, okay. Without using a calculator, determine the exact value of the following. So if you have negative exponents, make them positive. So how do I make this -3 positive? Okay. And what is 2 cubed? 8. So this becomes 1/8. Somebody verify that for me on a calculator and tell me if you get 1/8. So 2 to the -3. Okay? With b, because I have this rational exponent, you're going to want to write it as a radical. So if I write it as a radical, what would go here? 2? Do I have to write the 2 there? No. Where would the 3 go?
Next. No, it would go outside.
I would probably want to put it outside, because if I put it with the 9, now I have to figure out what is 9 times 9 times 9. Can I do that without a calculator?
No.
No. Not to mention, even if I could do it with a calculator, could I then figure out what the square root of that number is? Can you tell me what the square root of 729 is? No.
At least.
So if I put the 3 on the outside, I get the square root of 9, which is 3. And now I'm going to raise that to the power of 3. So 3 times 3 is? 3 times 3 is? 9. And 9 times 3 is? 27. Okay? If you take the square root of 729, you get 27. And if you go 9 to the power of 3 halves, you also get 27. Make sure you put the 3 halves in a set of brackets, though, depending on your calculator. Some of your calculators will put exponents and raise them up. Some of the calculators will use that little, I call it a little hat. Then you have to put bracket 3 divided by 2. You need to know which calculator you have. What's 25 to the power of 0? Nope. 1. Anything to the power of 0 is 1. And the proof for that, I'll show you. If I had 4 to the power of 3 divided by 4 to the power of 3. My subtraction law tells me I can subtract the exponents, and I get 0. If I expand this out, my cancellation tells me I have 1. That means this has to equal that. And I could do it for any base and for any exponent combination that you give me. Okay. 16 to the power of -1/2. How do I make the -1/2 positive? Put it on the bottom. So I get 1/16 to the 1/2. And how do I work with that 1/2? Because I can't do to the power of 1/2 in my head.
It's just like square rooting.
It's just like square rooting. I change it to a radical. And what is the square root of 16? So if we look at the inverse of a relation or a function, so if we talk in terms of inverses with things that we know, what is the inverse operation to addition? Subtraction. Multiplication would be division. Squaring something? Square rooting. So the inverse kind of undoes the operation. So if I look at part 1, a function or a relation maps each element of set A, which we can call the domain, to the elements of set B, which we can call the range. So what I have is that I have set A is half of set B. So 1 is half of 2, 2 is half of 4, 3 is half of 6, 4 is half of 8. So the domain of this function is 1, 2, 3, and 4. The range would be 2, 4, 6, and 8. If I had to graph this in terms of ordered pairs, I'd have 1 and 2, 2 and 4, 3 and 6, and my last ordered pair would be 4 and 8. The inverse undoes this. So if I was to do the inverse operation, set B would now become my new set A. It would become my new domain. And then the domain, or my set A, would become my new range. So in other words, the elements of set B are mapped back. So the way that I could look at it is 2 is double of 1. 4 is the double of 2, 6 is the double of 3, 8 is the double of 4. So in terms of my ordered pairs, instead of having 1 and 2, I now have 2 and 1. Instead of 2 and 4, I would have 4 and 2. This becomes my new x's, these become my new y's. My next ordered pair would be 6 and 3, and then 8 and 4. Okay, so let's graph these. So let's start off with the first set. The first set of ordered pairs, which were just up here, 1 and 2, 2 and 4. So if I graph 1 and 2, 2 and 4, 3 and 6, 4 and 8. If I graph the other set, I'm going to do it in a different color. I have 2 and 1, 4 and 2, 6 and 3, 8 and 4. Once you're done plotting these points, join them together. So you can use a ruler, you can use the side of your calculator, try to join them in a straight line. The last part on this section says draw a mirror line which represents the axis of symmetry in this graph. In other words, draw a line that would become my reflection line. So we've reflected before over the y-axis, reflected it over here. We've reflected it over the x-axis. But is there a line that I could reflect this to this? Where would that line be? 0 to 10.
0 to 10, 10.
Okay, 0, 0 to 10, 10. Okay, so if I draw that line, and I'm going to change the color of it just so that it doesn't make it red. Does that look like my mirrored line? Yeah. The equation of this line, so Kyle's given us two of the points, 0 and 0, 10 and 10. What is the coordinate of this point right here?
5,
5, 5. If I said that I had a coordinate 3, what would be the other coordinate? 3. The x's and the y's are always the same value. So my equation is that y equals x. Because whatever x is, y is the same thing. 10, 10, 9, 9. If I start to get into decimals, it would be 9.5 and 9.5 and so on. Okay? So if we fill in this chart, this was my first function. So in words, I get half of. So 1 is half of 2, 2 is half of 4, 3 is half of 6, etc. My equation is whatever the x value is, to get the y value, I can multiply it by 2. And then my domain were my first elements, my x's, and my range were my y's. The inverse is the operation that undoes it. So that was the is double of. 2 is double of 1, 4 is double of 2, 6 is double of 3, 8 is double of 4, and so on. And then there's my new domain and range. My equation. What can I do to x to get to y? So what do I do to 2 to get to 1, 4 to get to 2, 6 to get to 3? Half it. So y would equal half of x. What if I didn't know how to get that equation? If the equation was more complex? Okay. Well, if you notice, what we did with the coordinates is we interchanged them. The x's became y's, the y's became x's. I can do that in this equation. So if I interchange, the x and the y in the equation, instead of y equals 2 times x, I have x equals 2 times y. Is that how I normally write equations, x equals? How do I usually write them? As a y equals. So in order to get y by itself, I need to get rid of the 2. How do I get rid of the 2? Divide by 2. So I get y equals x over 2, which is the same as half of x. The other way to look at this, remember what we said, inverse operations? So instead of dividing by 2, I can multiply by half. This would be the same. If I multiply by half, that brings me to this point here. Okay, so let's look at the next one. The first diagram shows the relation is the square root of. So what that means is negative 2 is the square root of 4, because negative 2 times negative 2 gives me 4. Positive 2 is the square root of 4, negative 3 is the square root of 9, and 3 is the square root of 9. So if I completed the second diagram to show the inverse of, the 4 and the 9 move over to the left-hand side. And then my negative 2 and positive 2, my negative 3 and positive 3 move over to the left-hand side. So if I filled in my chart for this one. The coordinates of the points, negative 2 and 4, 2 and 4, negative 3 and 9, and positive 3 and 9. I'm not going to worry about the equation for a moment. But I'm going to look at the domain. What's my domain? What are my x values? So what are all my x values? Okay, so if I wanted to put them numerically, I put negative 3 first because it's the smallest one, then negative 2, positive 2, and 3. Typically, we would list our domain in numerical order. And I should have actually my curved brackets on this. So negative 3, negative 2, 2, and 3. What's my range? What are my y values? So 4 and 9. So if I look at the equation, what can I do to 2 or negative 2 or negative 3 or positive 3 to get to 4 or to get to 9? What am I doing with that value? So what can I do to 3 to get to 9?
Square.
Square. So my equation would be y is x squared. So whatever the x value is, I square it, I get my y value. So now we're going to look at the inverse. So with my inverse, my new domain is my 4 and my 9. What's my new range?
Same as the domain.
Same as the domain from the previous one. And then my coordinates, 4 and negative 2, 4 and positive 2, 9 and negative 3, 9 and positive 3. Now I need to think of my equation and my relation in words. So what can I do to 9 to get to 3?
Square root.
And what do I do to 9 to get to negative 3? Same thing, I still square root it. So I get y equals the square root of x. So in words, 9 is the blank of 3. So in this last one, 3 is the square root of 9. 9 is the what of 3. 4 is the what of 2.
Multiple.
Okay, does that mean that 6 and 2 would work as well?
It's the square.
It's the square. So is the square up, not square root, the square? Okay, one last thing with this. If I was to do like I did above and I interchanged these things around, I could say that x equals y squared. X is the square of the y. 9 is the square of 3. That is what that says. Again, I wouldn't leave this as x equals y squared. I would rewrite this. How do I get rid of the square?
Square root.
Square root, so I square root the other side. A lot of times you'll actually see it written like this, a positive and negative, when I square root, because I'm not sure if I should be taking the principal square root in this case. And if I look at it, when I take the square root of 9, I am getting two possible answers. I am getting a positive 3 and a negative 3. Okay, so on the next page, we're going to plot these points. So I'm going to plot the original function in green, and those were my coordinates of negative 2 and 4, positive 2 and 4, negative 3 and 9, and positive 3 and 9. Remember, this relation was my y equals x squared. So if I wanted to add a couple of other points, such as when x equals 0, what's 0 squared? 0. If x equals 1, 1 squared is, and if x equals negative 1 squared is positive 1. So what I get is I get this curve shape. Do you remember what we called that graph? What shape we called that? Para something? Parabola. That's okay. You guys got it. That's good. So now if I was to inverse this. So when I inverse this, one of the points that I got is that when x was 4, y could be positive 2 or negative 2. When x was 9, y could be positive 3 or negative 3. So this becomes my new graph. And if I draw that mirrored line that Kyle talked about before with the 0 and 0 and 10 and 10, oops, missed that one. Does that look like my reflection line? Does this look like if I reflected this, it would reflect to here? It should. So remember the equation of that mirrored line was that y equals x. Whatever x is, y is the same. So if we finish completing this chart, the equation of my original function was y equals x squared. The domain of that function, that's the function I have in green. What are my possible x values? What happens to this parabola as it extends up? What does it keep doing?
It's wider.
Keeps getting wider and wider. So the question to ask when you're looking at domain, is there an x value that I can't have? So could I have an x value way over here? If this keeps getting wider and wider, I don't mean on the axis. Could I follow it up?
Yes.
And if I went way over here and followed it up, would I hit the graph? So is there an x value that I can't have? No. So how do we express that? What do we say? X can be what? Any real number. So I can do that two ways. I can write it this way. That was my set builder notation. Or the other way I could write it is I could say x can go from negative infinity to positive infinity. And what would I put for brackets?
X.
So this is interval notation. So when I do my interval notation, I can either use square brackets or curved. How do I know when to use the square brackets? Pardon? When it stops, when it equals that number. Do I know what negative infinity is as a number?
The smallest possible number minus 1.
Yeah, it's the smallest number you can think of minus one more. Or the biggest number you can think of plus 1. So infinity is not actually a number, it's more so an idea.
The biggest number plus minus the smallest number minus 1.
It is, because smallest number minus 1 would give me one smaller.
We said the exact opposite of things. Well, obviously, because it is.
So when I go to positive infinity, it's plus 1 because I get bigger. So. Okay. What's my range? What are my possible y values in this green graph? So in other words, what can't y be?
Less than 0.
Less than 0. So y has to be greater than or equal to 0. And it can be any real number bigger than that. If I was to do my interval notation, it would be going from 0 to infinity. Infinity would have a curved bracket. 0 would have a squared one because it could equal 0 this time. So now look at my blue graph. What are my possible x values?
Anything more than 0.
Anything more than 0. I don't have x values over here. So x can't be a negative number this time. X has to be greater than 0. What can my y values be? Yeah, they can be anything. Because this is just going to keep getting wider and wider. This is following our pattern. Domain becomes the range. Range becomes the domain. And if I look in terms of my graph, x has to be a number bigger than 0 because I can't take the square root of a negative number. Okay. Determining the inverse of a relation or a function. If a function or relation is defined by a set of ordered pairs, the inverse is defined by interchanging them. So if I give you a set of ordered pairs and I say find the inverse of this relation, you interchange them. If I give it to you as an equation, change the x and the y out for each other and then solve the equation for y. If I give this to you as a graph, you can reflect it over that mirrored line. If I give it to you in terms of domains and ranges, the domain of the inverse was the range of the original function, and the range of the inverse was the domain of the original function. So if we look at the last question, determine the inverse of the function defined by the equation y equals 5x minus 6. It's given to me as an equation, so to write the inverse of the equation, I interchange the x and the y. So I now have x equals 5y minus 6. I would not leave it like this because I always express my graphs as a y equals, otherwise I can't actually graph it. So how do I get x by itself? Or sorry, how do I get y by itself?
Isolated.
Okay, so how do I isolate? What do I move
Add
over
6.
first? Add 6 to each side.
Divide the 5 by 5.
So then divide by 5. So y would equal x plus 6, all divided by 5. Or I can split it up. X divided by 5 plus 6 divided by 5. Which I could clean up and write it as a 1/5 times x. The other way I could look at it from this point is I could multiply each side by 1/5. So there's my 1/5 x and my 6/5. I want you to do for practice question number 4 and then questions 6 to 10.